Now we're going to look at some general strategies for finding limits. A lot of times we have a function that's defined everywhere except one point. And of course that one point is where we're finding the limit. We're trying to find out what is the behavior of my function f at that one point where it's not defined. Suppose I can find another function g, and g agrees with f at every point except x equals c. Then it turns out if f and g agree at every point except x equals c, then the limit as x approaches c of f of x is the same as the limit as x approaches c of g. Now we're going to use this in practice more than a direct application. Now let's look at some strategies for finding limits. The first thing you always do is plug in. Just do direct substitution. If direct substitution gives you an answer, stop, you're done. Now, a lot of times, direct substitution is not going to work, and so we need to find another function so that g of x, so that f and g agree with each other at every point except x equals c. And then, of course, we can use theorem 1.7 to say the limit as x approaches c of f is equal to the limit as x approaches c of g, which is g evaluated at c. And the last thing you can do is use graphs or tables to reinforce your conclusions. Now, we're going to do these periodically. The AP board absolutely loves graphs and tables. Let's look at this function right here. The limit as x approaches 1 of x cubed minus 1 divided by x minus 1. The first thing, let's try direct substitution. So this is 1 cubed minus 1 divided by 1 minus 1, which is 0 over 0. And this is bad. We cannot do this. We're going to stop there. Let's try to find another function that's equivalent to this. Now, whenever you have a polynomial as a denominator, think of factoring. So let f of x equal x cubed minus 1 divided by x minus 1. Now I'm going to manipulate this a little bit. I'm going to factor x cubed minus 1. And of course that's x minus 1 times x squared plus x plus 1. And so I'm going to, let's see, I'm going to divide this by x minus 1. And those are going to go away. So I'm going to define g of x as x squared plus x plus 1. All right, so now I have two functions that are equivalent at every point except x equal 1. So I can now conclude that the limit as x approaches 1 of f of x is the same as the limit as x approaches 1 of g of x, which is 1 squared plus 1 plus 1, or 3. So I'm done.